Right, this is the next lesson in the sequence of lessons that are for Chapter 9 of the A-Level Maths Pure textbook for Year 13. And what we're going to look at today is looking at differentiating using the chain rule. Now, you'll find the chain rule incredibly useful because it opens up differentiation to a lot more complicated functions than we have been able to differentiate before. Okay, so it's going to be a very useful thing to have in your tool belt. Now, if we have a look at where it fits in with what we've done already and what we've got left to do, we've done differentiating trig functions. Remember, we did sine and cos. We last lesson did differentiating exponentials and logs. Now, what we've got left to do, this is going to be over 3 lessons. We've got using the chain rule, which is what we're going to do today. We've got the product rule, and then we've got the quotient rule, okay? And then the subsequent things in this differentiation chapter, which is quite a large chapter, we will then pick up when we start lessons again in September. Okay, so let's have a quick recap of things that we've done so far. So things you should know: if I've got a function which is a equals say sine kb, now I've purposely just put some different letters in here just to make sure you understand. So my a here is equivalent to my y, and my b is equivalent to my x. So when I differentiate, it's going to be dA dB, because a is the thing I'm differentiating, and a is a function of b, so that's the variable, k is a constant. Now remember, when we talked about this, sine differentiates to cos. Always leave the argument the same. I emphasise that in the lesson. It's sine of something, it's cos of that same thing, but remember we put a k at the front. If we've got c equals cos kd, again remember c is like your y, so it's dc dd, because this is my variable. And remember, cos goes to minus sine. You need to remember these because they're not in the formula book. Okay, same variable, so cos of something is minus sine of the same thing. And then we have a k at the front. Okay, final one is our exponentials. So again, if we've got big E equals e to the power kf, I'll do dE df. And what we've got here, remember, e to the power something goes to e to the power something, but then we get this extra k at the beginning. And the chain rule will really explain why we get these extra numbers at the beginning, because actually doing that is part of the chain rule. Okay, so let's have a look at our definition of the chain rule. So you'll need to write this down in your notes, okay? And what we use it for is to differentiate composite functions, or a function of a function, okay? And you know, something like sine kx is actually a composite function, okay? Because the original function would just be sine x. Okay, so by introducing the k, we've made it a composite function, or we've made it more complicated. So this is what the chain rule looks like. Okay, so if you've got y as a function of u and u as a function of x, okay, then if I do the chain rule, I can do dy dx as dy du times by du dx. And what you can think of with this, mathematically it doesn't really work like that, but it's a good way of thinking about it, is thinking about these du's kind of cross-cancelling there and ending up with dy dx. So that's quite a nice way to think about it if you're trying to work out or remember what the chain rule is. Okay, so make sure you have that written down. We'll do some examples so you can see nice and clearly what I mean by what y is and what u is. Okay, so just hold that thought for a minute, make sure you have those written down. Okay, right, so here's our first example. Now, from what work we've done before, we know that if we have y equals sine 4x, then dy dx is 4 cos 4x. We know that already because sine goes to cos, same argument, times by 4. But let's see why that is the case. Okay, so if we have a look at our chain rule that's up at the top here, so what we're saying is y is a function of u. Okay, so what I need to do, okay, is I need to write y equals, what is my base function that I'm working with? It's sine. Okay, so y is equal to sine of something, and that something here, that is basically my u. Okay, so y is equal to sine u, where u is 4x. Okay, so can you see I've kind of split it into two separate functions? Okay, my first function is my function y, which is basically the overall function. It's sine for this one. For the next one, it will be e to the power. It could be raising something to a power. It could be a variety of things. But it's basically that 4x becomes my u. Now, let's have a look at my chain rule then. Two things I need to do. I need to do dy du. So basically, I need to work out what is the differential of my base function. Okay, we know sine of u goes to cos of u. Okay, I also need to do du dx, so I need to differentiate what my second function is, because if you imagine you did this as two functions, if you input x, you do function u first, you times by 4, and then you put it into function y, so you do sine of that. Okay, differentiate du dx and we get 4. Okay, so by our chain rule then, dy dx is equal to dy du times by du dx. Okay, I'm just going to simplify my answer. I'm going to put the 4 at the beginning, and because my original function didn't have a u in, I'm going to replace my u back in with what u was, which was 4x, and you can see that I get exactly what I was expecting to get. Okay, so can you see how that composite function, two things going on, times x by 4, then find sine of it, splitting it into two separate functions, differentiating those individually, and then timesing them together. That's what the chain rule is all about. Okay, so let's do this next one then. So for this one, y is equal to, well, what's my basic function that's going on here? It's e to a power. So I make this my u, e to the power u, so where u equals 3x. Okay, so my two functions are take x times it by 3, then do e to the power of it. So I've split it into two. So let's do my dy du first. Dy du, remember when you differentiate e to the power, you get e to the same power. Okay, and my du dx, differentiate 3x, I get 3. So again, by my chain rule, I get dy dx is equal to dy du times by du dx, put the 3 at the beginning, and then rather than writing u as my power, replace it by what it was originally, and I get what I'm expecting. Okay, so that's basically how the chain rule works. Okay, it splits your function. Okay, so far we've looked at the composite functions. There's sine of something more complicated than x. You can similarly have cos and other things as well. We've got e to the power of something that's more complicated. Let's look at another composite function, this one here. So this here is my composite function. Now you think about what you would do if you were evaluating y. You put in your value of x. Okay, there's two things you do. You do your 3x to the 4 plus x, and then you'd raise it to the power 5. So when you've got some bracket raised to a power, this is what is going to be my u. Okay, that's my bit I'm going to do first. So if I split it like I did on the previous examples, y is equal to u to the power 5, where u is the thing that's in the bracket, 3x to the 4 plus x. Okay, so you're happy with that? So the previous page, remember, we had sine of something, and the bit in the bracket became the u. We had e to the power something, and the power became the u. For this one, where we've got a bracket raised to a power, it's the bracket that becomes the u. Let's do our differentiation then. Dy du, remember differentiation? Bring down the power, reduce the power by 1. Let's differentiate the thing in the bracket. Bring down the power, so 12x cubed plus 1. Okay, so using my chain rule, dy dx is equal to dy du times by du dx. Now, because that's got more than one term, I'm going to stick it in a bracket. To state my final answer, I need to not have any u's in it. So let's replace my u back with what I defined u to be, which is basically the thing in the bracket. Okay, and then next to it, I've run out of room, but you can just write it next to it. I've got that. Okay, so that would be my answer, that times that. Okay, now you can use that as your method, and that's a perfectly fine method to use. Okay, personally, I think you should be able to do it without specifically mentioning what your u is. So I'm going to now show you how I do these. Okay, so where I've got my function y equals 3x to the 4 plus x to the power 5, I decide when I look at it what is going to be equal to u. Okay, I can put a box around it if I want and call it u, but I'm not going to specifically write it out necessarily. Okay, so I would have y equals u to the 5, where u is equal to that. I'm going to go straight for my differentiation though. Okay, so I'm going to visualize in my head that this is u to the power 5. How do I differentiate u to the power 5? I bring down the power. Instead of writing u, I'm going to write my bracket because that is what my u is. So I bring down the power, I reduce the power by 1. So that is my 5u to the 4, but without specifically calling it u. Okay, here's the bit that you need to remember. So this is me then saying I'm using the chain rule. So I've done 5 times the bracket to the 4. By the chain rule, I have to times by the differential of the bracket, or what's equivalent to your du dx. So that is going to give me my 12x cubed plus 1. Okay, so this bit here is equivalent to my 5u to the 4. And this bit here is equivalent to my du dx. But I can go straight from that to that just by thinking to myself, what is my u? This, I think, in lots of questions, just makes your life a bit easier if you can get straight from that to that without having to write all of this down. If you find, I'd say have a go. If you find that you can't get the right answers for them, then of course go back to specifically writing out the separate bits and doing it like we did up here. I think the majority of you really should be able to do it like this. Okay, it's a much cleaner and neater way of doing it by keeping it all together. And all I'm doing is I'm saying, this is my u, okay? So 5u to the 4, and by the chain rule, this is my du dx. Okay, the only final thing I do is I get rid of the times sign and I just write my answer down, just like I did for the other one. Okay, it's just tidier without the times sign in it. Sometimes you need to simplify things a bit, but there's not a lot I can do with that. Okay. Right, so coming up on the next slide then are 4 that are like this. So what I'd like you to do is write down this first one and have a go at doing it like I showed you. Okay, so write down y equals 1 plus 2x raised to the power 4. Okay, so it's a bracket raised to a power. If you want to indicate what is your u, okay, the thing in the bracket is my u. So that's the same as y equals u to the 4. Okay, so without specifically writing what u is, how do I differentiate u to the 4? Bring down the power. write the bracket because that's my u, reduce the power by 1, so bring down the power, reduce the power by 1. Here's my chain rule bit. I always write a nice big times because it's chain rule now, okay? I'm now timesing by du dx. What's du dx? 2. So that one I would tidy to give me that. Okay, so do you see how we can write these down without specifically saying what u is, just by picturing u being the thing that's in the bracket? Okay, I just think this is such a sort of neat way of doing it and an easy way of thinking about it. You know you're using the chain rule, okay, so you bring down the power, reduce the power by 1, and then the chain rule bit is timesing by the differential of the bracket, which is your du dx. Okay, right, next one then. I'd say write it down and pause this. Okay, so this bit here is your u. You can label it as u, or you can just visualize it as u. So what do I do when I differentiate? U to the half, bring down the power, you get a half u to the minus a half, bring down the power, reduce the power by 1, big times sign. I then times by du dx. Du dx is the differential of the thing in the bracket. Let's tidy. 4 times half gives me 2. Okay, and unless it's to show that they're completely happy with you leaving as that to the power minus a half, that's fine. Okay, it's 2 over the square root of that, but that doesn't matter. Okay, next one. Right, that is something to a power. Okay, what power though? Square root. Lovely, a half. So again, write that down, pause it. Okay, this bit in my bracket is my u. So when I do dy dx, what do I do? Bring down the power. That's my u, so I'm just writing it. Reduce the power by 1. Nice big times sign because it's the chain rule. Times by du dx. Do be careful with this, these are quite often forgotten. If I differentiate that, I get minus 1. Okay, so altogether I get a minus a half, 7 minus x to the minus a half. Okay, that's your answer. Cool, right. Final one then of this type. So again, we've got something in a bracket raised to a power. So visualize, this bracket is my u. So differentiate then. That's like differentiating 3u to the minus 6. Bring down the power. There's a 3 at the beginning, so that becomes a minus 18 at the front. Careful with your signs here. Reduce the power by 1, that becomes a minus 7. Big times sign, okay. This is your times by du dx. What's the differential of the bracket? Gives me a minus 1. So just be really nice and accurate with that. Tidy it. Get 18, 8 minus x to the minus 7. Okay, so what do you reckon? Do you reckon you can write those out without specifically saying what u is and doing the dy du dx? I reckon so. I reckon you can, okay? And this just makes your working really nice and neat. Yes, you're using the chain rule because you've identified what u is, okay? You've brought down the power, you've reduced the power by 1. Okay, you've not written 4u cubed, but you've just written 4 and then the thing, or the bracket, cubed. And then remember the big times by du dx, which is the differential of the thing in the bracket. Okay. I reckon you can do them like that. Right, let's have a look at another one then. Here we go. Given that y equals sine to the power 4x, find dy dx. Okay, right, let's have a think about that. Composite functions then. Okay, now the trouble that you get with sine and cos functions is sine to the power 4x is actually the same as that, isn't it? You evaluate your sine x and you raise it to the power 4. We just find with our trig functions that it's neater to put your power next to the trig function rather than using a bracket. So what are our two functions going on here then? If we put x in, what would we do first? We'd find sine of it. What would we do second? We'd raise it to the power 4. So this, although initially it didn't look like it, this is of a similar form to the ones on the previous slide where you've got something raised to a power. So what's going to be u? It's going to be my thing that's in my bracket. Okay, so let's do our differentiation then. We've got something raised to a power. How do I do something raised to a power? I bring down the power. I reduce the power by 1. Okay, so I think sometimes writing it in the bracket like that rather than like this can make it a little bit easier for you to see what's going on. Bring down the power, reduce the power by 1. Chain rule, what do I times by? Du dx. What's du dx? That's right, cos x. So what's my final answer? 4. I'm not going to write the brackets because we normally would write that as that. And I can just write those next to each other without a sign, without a times sign in. Okay, so can you see with that one what's going on? Very, very useful, the chain rule. It enables you to differentiate some really quite complicated functions. Okay. Just remember with your trig functions, if you've got it raised to a power, that's the same as having it in a bracket raised to the power. So that's the technique you use for those. Okay, we've got a few slightly more complicated ones. So onwards and onwards, here we go. Let's have a look at this. Now, the first thing you need to do is think about what is your u. Okay, and so write out the question and what you can, if you want to, I sometimes do with things like this, is say, that's my u. So I've made a conscious thought of what my u is. Okay, so this is an e to the power something. So differentiate. Okay, so e to the power something, what do I get when I differentiate? E to the same power. Okay, if I had e to the u, it would go to e to the u. What do I times by? Du dx. What's du dx? Minus sine x. So I think maybe, especially when you start doing these, maybe actually drawing a little circle or a little box around the thing that's u might be useful for when you're working out the du dx. All I'm going to do is pop my sine x at the beginning and then my e to the cos x at the end. Okay? Right, and ln. Okay, what's my u here then? I think it's going to be the thing in the bracket here, isn't it? So it's ln of something, so it's ln of u. Okay, now when I differentiate, what do I get if I differentiate ln of u? Do you remember what ln differentiates to? Yeah, differentiates to 1 over u. Okay, or it differentiates to 1 over u is my sine x. By the chain rule, what do I times by? I times by du dx. What's du dx? Cos x. Now, I'm going to write it like this and just point something out to you. By the chain rule, okay, when I differentiate ln of something, okay, so this is a general one to remember. If y equals ln of some function of x, then my differential is the function of x on the bottom, because I do 1 over, and then the differential of that on the top. Okay, that is a really useful thing for you to remember. You can see why that's the case where we've done the chain rule here. But if you just remember that, you can use that every time when you do lns. So when you do lns, it's the differential of the thing in the bracket on the top, and then the thing in the bracket on the bottom. How can I write cos x over sine x? 1 over tan. Do you remember what 1 over tan was? Cot. Okay. So do remember that bit with your lns. Okay, next one. Sine of something quite complicated. Well, what's going to be the u? The u is going to be my thing in my bracket. So dy dx. If I differentiate sine u, what do I get? Cos u. So I'm not going to bother writing u, I'm just going to write cos of. Notice with your trig functions, it's always the same argument. It's a horrible argument, but it's always the same argument. What do I times by the chain rule? Du dx. Okay, so let's differentiate that. What do I get? 6x minus 2. Multiple terms, must stick it in the bracket. Okay, just write my answer a bit neater. I'd probably put that at the front. Okay, and then just write that like that. Okay, so notice, remember, when you differentiate trig functions, never change the argument. It always stays the same. Sine goes to cos of the same thing, by the chain rule, times by the differential of the thing in the bracket. Right, my final one then, here we go. This is going to be my u, so it's cos of u. So straight into my chain rule. Cos goes to minus sine. Don't change the argument. Okay, minus sine of the same thing. Big times sign. What do I times by the chain rule? I times by du dx. How do I differentiate e to the 2x? It's actually another chain rule, isn't it? 2e to the 2x. So sometimes you have to use chain rule within a chain rule. Okay. So let's just put the e bit at the beginning. There we go. Okay, so if you're not sure about any of those, just rewind a little bit and watch them again. Okay, the key thing is identifying what is your u, differentiating that function, so e to the something goes to e to the something. Okay, sine of something goes to cos of the same thing, cos of something goes to minus sine of the same thing. And remember this with your ln. Okay, ln goes to 1 over the thing in the bracket, but by the chain rule you times by the differential, so you end up with this really important thing to remember for lns. Okay, right, one last bit then. Okay, we've used this once before in a different question. Okay, if I work out dy dx, okay, then how does that relate to dx dy? Well, it's 1 over. It's a bit like taking the dy dx and turning it upside down, because the rate of change of y with respect to x is the same as 1 over the rate of change of x with respect to y. Now let's see why that's useful then. Here's a question that I want you to write down. So it says find the value of dy dx, the gradient, at a particular point on this curve. Now notice with that curve, it's not written as y equals something, it's actually written as x equals something. And it's really not easy for us to rearrange it to get y equals something. So if we end up in that situation where it's written kind of the other way around, by far the easiest way to differentiate is by, instead of doing dy dx, doing dx dy. Okay, if I do dx dy, bring down the power, reduce the power by 1, and y goes to 1. Okay, so if dx dy is equal to that, that means dy dx is equal to 1 over that. Okay, I want to evaluate it at a particular point. Thing to be careful here, notice my gradient function is actually a function of y, so do make sure you put in the y value, not accidentally the x value. So if y is 1, dy dx equals to 1 over 3 times 1 squared plus 1, which is a quarter. So when you're given functions, it's much easier if they happen to be written in the form x equals something, and it's not easy to rearrange them. Do dx dy, and then to find dy dx, flip it upside down. Okay, that's all from me. Here are the questions for you to do. It is quite a lot of questions, but you need to practice them. This is a really important skill to master, okay? And you do that by getting lots of practice. Now, what I'd say to you for each of these, write out the question, write it as y equals something, and then dy dx equals something, okay? So write out the question first. Have a think about what is going to be your U. I would say try and get to grips doing it without this, all right, just by labeling on your question. So here's my question I'm doing, something like that to the power of 5. Think about what your U is, even write what your U is, okay, and then do your differentiation. So bring down the power, reduce the power by 1, write that thing in there, by the chain rule times by the differential of the bracket, and then simplify. Okay, I think you can all do it like this. Okay, it just makes your life a little bit easier. So have a good go. Make sure you work through all of these. They're not to be handed in, okay, but make sure you work through all of them. Okay, right. Well done then, and good luck with those.